let's go through some examples of using the work-kinetic energy theorem. So as a reminder, work net overall done by forces acting on an object is going to equal the change in kinetic energy, meaning the final kinetic energy minus the initial kinetic energy. And we know kinetic energy is 1/2 mv squared, where m is the mass in kilograms, v is the speed at which the object is moving. So that's what we're going to use to solve a few problems. So here we have our particle. It's initially at a position of 1.25 meters. So this is our x initial. It is moving at 2 meters per second at this moment. So that's our v initial. As it moves, it experiences a force given by this equation. So this is a varying force. We want the particle's speed when it reaches 3.5 meters. So this is our x final. So to relate forces and speeds together using this new concept of work and kinetic energy, we're going to say that the work done by this force specifically, the particle's moving in the x direction. So even if it's on a surface, the normal force and the force of gravity will not be doing work, and that's because they are perpendicular to the motion. So the work done by this force will equal the change in kinetic energy, but I'm going to go ahead and substitute in our 1/2 mv squared for kinetic energy. So we'll have a final 1/2 mv squared and an initial 1/2 mv squared. So to relate this force to the speeds, we'd need to be able to calculate this work first. So work, we know, is the integral of force dotted with displacement. And again, the dot product means the force parallel to the motion is what matters. So this force, since they give us a subscript of x, it's implying this force is acting in the x direction. So we could actually write this as the integral of this force that is in the x direction, specifically times dx. Dx meaning these infinitesimally small little positions as we move along the x-axis. So let's put in function. Our limit will be from the initial position, so that 1.25 meters, to the final position of 3.5 meters. So as we integrate, we're going to get 0.35 over 3 x cubed minus 0.138 over 2 x squared. And we need to evaluate it between these two limits. So plugging in the upper limit first. And then we'll need to subtract the lower limit plugged in. All right, so plugging this in my calculator. I'm going to do this in increments. So the first term I'm getting 4.15 6, 8. Subtracting off the second term. The second term's not very big. So when I subtract these, I'm getting a work of 4.037. This is in joules. So as soon as we have completed the integral, that is the work done. Coming back now to relate this to the speed, we have the work. Well, maybe I'll solve this symbolically first. So we have V initial. So I'm going to bring that to that initial kinetic energy to the other side. And we're solving for V final. So if I multiply both sides by 2 and divide by m, and then the square root, this will be how we calculate V final. So 2 times this work over the mass. Now be careful, this mass does need to be in kilograms. So 0.15 kilograms plus the initial speed they told us was 2, so that needs to be squared. So let's see. I'm getting 7.60 meters per second. So this particle speeds up because the work done on it is positive, meaning energy is added to this particle. I guess I didn't mention that before. We do want to choose our system, as we've talked about in earlier videos. In this case, the system is simply the particle moving along, and the work done on that particle determines how fast it will be moving finally.